series on astrophysics. Today we are happy to have Dr. Wang taking us to the long march from supernova to gamma ray burst.
Okay, thank you.
Yes.
Yes, my talk is titled "Long March from Supernova to Gamma Ray Burst." So let's first go back to the history. In the year of 185, that year was quite turbulent. That 1 year ago, the most famous revolt in China, that the Huangjingqi started, and it spread like a flame. And in the early year of this 185, on February, there was a flame burned down the palace of in Luoyang, which was the capital of China. Then the emperor wanted to build a new one, a more fancy one, and he started to charge additional tax. So people was suffering, and they wished something to be changed, some change can come. And it was on December 7th, 185 AD, that is a symbol of the change came from the sky. That a burst which was like 100 million times brighter than the star appeared on the sky, and it lasted 8 months, as written in this book, Hou Han Shu. And it was another day in history in 1054 that another star appeared. Now, that time people were walking in the marketplace discussing the gossip that the barbarian troop advancing to the north of China. But in a sudden, also a very bright star appeared on the sky, and it was the daytime. And this star was visible for hundreds of days during the daytime. And many books wrote this history. And the previous one, this one, was the first supernova that on the record. And this one, of which its remnant becomes very famous. I think we can say it's the most famous remnant that is called Nebula in the history of human being. Then in order to understand the supernova, first we need to have some knowledge of the star formation and the evolution. Stars are formed by gases, where you have a lot of gases. For example, in a given region, the density of the gas exceeds a limit, and the gravitational force will compress the gas to very, very thick. And in the center, if the total mass of the gas is more than 0.08 solar masses, then the hydrogen burning will be ignited. The hydrogen burning takes a very long time. For our sun, it takes more than billions of years. But for example, this star, the 25 solar mass star, it takes a short time, about 7 million years. After burning the hydrogen, first we have almost totally hydrogen. So the core will be something like hydrogen produces helium, so we will have a helium core. And on the very outside layers, because the temperature is not very high, so there are some hydrogen remain there. So you will have a layer of the hydrogen. Then after burning the hydrogen, the star collapses again, and the temperature in the part gets higher and higher. If the total mass of star is more than 0.05 solar masses, the temperature will be enough to ignite the burning of helium. The helium produces carbon oxygen. Then this procedure continues. But if the star is less than 8 solar masses initially, the helium will produce the carbon oxygen, but carbon oxygen cannot reach high temperature enough to burn to the iron. So we will have a white dwarf remain. In the very inside, it's the carbon oxygen. Outside, you have a helium layer and the hydrogen layer. This is one example of the white dwarf. It's this inside. This white point is a white dwarf. And the emission of this green and the blue part are from the oxygen and the carbon, and outside it's helium and the hydrogen. This nebula, we call it planetary nebula, will be disappeared within thousands of years because they are expanding outside. And finally, only a white dwarf remain here. And we know that most of the stars are in the binary system. So when we have a white dwarf here found and another companion star outside, but during the evolution, the orbital motion of the two stars will emit a lot of gravitational wave. Then the gravitational wave takes a lot of energy out. So the orbit will be shorter and shorter. So finally, the gravitational field will influence these two stars. So the mass will be transferred from one star to another, this one. And when the mass of this white dwarf exceeds the transelectrical mass at 1.4 solar masses, this star, the nuclear reaction started again. Then you will have the carbon oxygen burning to the iron group. And this is a remnant of the first supernova that we introduced in the first slide. It's RCW86. This is a remnant of this supernova 15185. But from nowadays, when we look at that position written in the ancient book, we found this red part, which has a previous hydrogen. This is helium. This is helium in the optical and infrared. And also we have this blue and green emission are in the X-ray. This X-ray emission comes from the shockwave sweeping the interstellar media, and it has synchrotron emission. Synchrotron emission usually is at the high energy, so it's in the X-ray. So from the distance, the radius of this system is ring, and also we know the velocity of the shockwave. We can infer how long it took. So from a shockwave in the center propagating to the boundary. Therefore, we know the age of this system. So we found the coincidence of the location and the time. Then we identify that this remnant comes from this supernova, the first supernova. So if the initial mass of the star is more than 8 solar masses, the electron's degeneracy force cannot prevent the collapse anymore. So we will have the oxygen and the carbon burning to the iron class including the nickel, the cobalt, and the Fe iron. It takes a very short time, we see here, some months. Also, we know that the binding energy of the iron group is very high. It's the highest binding energy. So the Fe, the iron group, cannot have the nuclear fusion because it needs to absorb energy to continue. But always the system tends to be in the lowest energy state, so the fusion stops. So when this center, so we will have a very, very thick, compact iron center, and something is falling at the moment because when it reaches the transelectrical mass. So this falling of the matter will be bounced back, but you cannot have the nuclear action, and so you cannot burn anymore. So some bounce back. This bouncing back produces a lot of the shockwave, very strong shockwave moving outside. Also, a lot of neutrinos strengthen this shockwave. So first, we will see the shockwave propagating inside along all these layers. Then it goes out. All these layers will be accelerated by the shockwave and be ejected. And we call this supernova ejector. So here is one example of the core collapse supernova. We call this type of core collapse supernova. And in the inner center, we have a neutron star remain. The neutron star, that is the degeneracy force of the neutron counteracts the gravitational force. And this is a remnant of that second supernova that I mentioned. This is the Kerr Nebula. So you may see a lot. This is from optical and infrared. And inside, this is a Hubble telescope, observed it. And inside, it's from Chandra telescope. It's in the X-ray. you miss something rotating here. This is a signal of the pulsar that is a neutron star fast rotating. So before going to some professional facts, that we first introduce this is a light curve. But in astronomy, when we see something, we always analyze two things. One is a light curve, another is a spectra. So light curve gives us the information of how bright it is at a given time, at a different time. For example, these the green points are the X-ray. So how bright is the X-ray emission at 100, at 1,000 seconds? The photons from the supernova and from the GRB has a very wide range of the wavelengths. It's from here, from the radio to the gamma ray. This is the spectra of the Carbon Nebula. You can see it's from this is the radio part, and this is ultra-high energy part. It extends more than 20 orders of magnitudes. So before we mentioned that we have two classes of the supernova. The first is for the low mass stars. We have a white dwarf. The white dwarf will experience the thermonuclear reaction, and it explodes. So this is thermonuclear supernova. If for the massive star, the more than 8 solar masses, it has the core collapse and form and a neutron star inside front. And historically, also we make this classification by the emission lines. So when we obtain the spectra, if the spectra has some evidence of the hydrogen, we call it type 2. If there's no hydrogen, we call it type 1. And now we are going to concentrate on this type 1b and type 1c. They are called collapsed supernova, but they don't have the hydrogen line, even they don't have the helium line. This is an example of the supernovae. Now, always there's a question that are supernova type 1b and the type 1c, they have the same origin, but this is still on the debating. Because the supernova 1b has hydrogen absorption, as you can see here, this orange part. But supernova 1c misses it, all of this structure, but it has a very small, the Si2 line. So some people think that type 1b and type 1c is just a continuity of a system, that one has lost more hydrogen envelope and one lost less hydrogen envelope. But how to lose this layer, the hydrogen one, hydrogen and the helium? There are two common ways. First is by the wind. If a star is very massive, then this star will have very high temperature, so it emits a lot of photons. This photon expels the outer layers, but it requires really high mass of the star, I think more than 35 solar mass at least, to remove this hydrogen layer. And there is a simpler way that if two stars are in a binary system, and the companion star peels, because there, for example, you have two stars, and the outer layer of one star, for example, the helium layer, are accreted to the companion compact object. But not all the mass are going to be absorbed by the companion object. As you can see in the animation, a lot of them are expelled to the galaxies, to the outside.
Is that real simulation?
This is a simple simulation, very simple simulation. It's real. And for the stars in the binary system, we don't require a star to have very big mass. You can have 10 solar mass, 20 solar mass to lose two layers, hydrogen layer and the helium layer. So when we pay attention to the observation, first, because we want to ask.
Before we now speak about the hydrogen and helium layer, which are stripped.
Yes, stripped, yes.
Good.
So now we ask, because for the type 1b and type 1c supernovae, we did not see the hydrogen layer and also the helium layer for type 1c. So they have two possibilities. They can be formed from a very massive star, or they can be in the binary systems. So let's see the first possibility. That if they are formed from a single massive star, then the number of the massive stars is not sufficient to account even half of the observed type 1bc supernova. And the second, that if it's from a massive star, the massive star is very bright. In principle, we should observe the progenitor, the massive star. But actually, we did not see so many. Are they from the binary systems? First is because if you have a massive star, you eject more mass, and if you have a low mass star, the ejector is less massive. The inferred low ejector mass of the supernovae 1bc is in favor of the binary scenario than the massive star scenario, because not so much mass was ejected. And also the supernova 1bc frequently shows a highly polarized and high velocity CA2 features. This is similar to the white dwarf type 1A supernova, which has a binary origin. And also we saw one example of the type 1b supernova, because Hubble did a lot of surveys of the sky. After observing this supernova, it examined the previous picture, and it found a missing star. That missing star was 10 to 20 solar masses. So it's the middle mass, not very massive. And also it favors the binary origin. So the conclusion is mostly, if not all, supernovae type 1bc arise in binary stars. Now we ask one question further. And we know the binary system. There are a lot of types of binary systems. You can have white dwarf, neutron star, massive star. And we are going to look at this system that we have a neutron star and we have a stripped core, which is made of iron, carbon, oxygen. And the answer of the evolution of this system leads to the gamma ray burst that we will talk later. Gamma ray burst is very much energetic. Here let's count the zeros. For a normal human being, we are using 10 to 9 erg energy per second. And the total electricity consumption is 10 to 19 erg per second. And for the Hiroshima nuclear weapon, it was 10 to 20. But I was surprised that 10 seconds of electricity used in the world is equal to the nuclear weapon, nuclear bomb. And the sun, our sun produces 10 to 33 erg per second, and the miracle is 10 to 43. But for gamma ray burst, it is 10 orders magnitudes higher than the luminosity from the Milky Way. 10 to 10 is the number of the total galaxies in the universe.
What do you mean by human?
By human is we are.
Infrared or infrared emission?
Or you eat the food. You just
No, I mean,
not infrared. All the effort. So the gamma ray burst itself, the luminosity is equal to the total luminosity of the universe. So it, per second. So it outshines. For 10 seconds. But the duration is very short. So it outshines all the universe. This is the real observation of this gamma ray burst 080319b. So let's see it. It is very bright, and we can see it if you were lucky that day. You can see it by your naked eyes. It's here. It's here, this part. This is a light curve, so it arises, evaporating, becomes very bright. Then after 50 seconds, this is in optical, it starts to decay. And finally, it fades out. Let's wait a moment. And this star, this GRB, occurred 7.5 billion years ago. So the light of it traveled half of the universe and reached us, but still we can see it by our eyes. So it's how bright it is. And the gamma bursts have very wide distribution in the universe because it's very bright, so we can see. Even it happened in the dark age. This one. This is the furthest one, GRB 04090423 at the redshift 8.2. It's about 600 million years after the Big Bang. So it's in the dark age. We can explore the characteristics of the dark age from GRBs. Nowadays, we have thousands of GRBs. So from this the lowest, the nearest one, and these two are the GRBs we are going to talk about. So by tracing the evolution of the gamma burst, we can understand the universe, even here. And now every year, after the launch of satellite of Fermi and Swift, we can see around 120 GRBs every year here. Before, because we did not have so strong telescopes, so the numbers are few. And this blue is the GRBs with measured redshift, which means we know the distance. So about 30% of GRBs, we know the distance. And this is T90, the histogram of the T90. T90 means 90% of the energy released in such a duration. By fitting this distribution, we can use two Gaussian distribution, and the division is at about 2 seconds. But later, we call this group the short one. We call short duration gamma burst, and this long duration gamma burst. They have different origin. And in 1998, there is a special event happened. In the position of a gamma burst, after 15 days, it appeared supernova 1c at here. This is the first gamma burst supernova association that we have observed. And later on, nowadays, I think we have like around 50 observations of this association. This is a light curve, so the time and the luminosity. We know that 90% of energy is released within a few seconds, but the rest of the energy is released for a very long duration, can be months or years. This is optical. And for the GRB, it decays following a power law usually. But at 10, 20 days, you can see a bump here. This bump is contributed by the supernova. This is a supernova contribution. So in this way, from light curve, we can recognize that a supernova occurring here. Also from the optical, if it's very close, we can see it directly by the image. And now you see here is a zoom of a lot of these light curves. At 10, 20 days, there are the bumps. And from the Doppler factor of the emission lines, we said that there are a lot of elements produced during the stellar evolution. We can infer the speed of the supernova ejector. The supernova ejector, the speed of the supernova ejector associated with the gamma burst is generally higher than the normal supernova 1c, which means the ejector has been accelerated. And if we assume that the mass of ejector for the GRB or for supernova associated GRB or not associated GRB have the same mass, then the kinetic energy in the supernova associated with GRB is about 2.6 times more than the normal supernova 1c BL. So from the previous discussion, we know that the progenitor of the supernova type 1bc mostly are middle mass stars sitting in the binary systems, and some type 1bc supernovae may originate from the massive stars. This is also, we keep this possibility, but also we know that the majority of the massive stars are also found in the binary systems. So the type 1bc supernovae prefer this binary origin. And also from observation, we know all the gamma bursts associated to supernovae are type 1bc, and their location, they have very similar prevalence of the location with low metallicity and a white dwarf host galaxy. So they are strongly associated. So now we ask, can that gamma ray burst occur in the binary system? So we go back to continue this image, and we will do some theoretical work on the evolution of this system, then compare with the observation. So we have a neutron star here, and we have a stripped core white FCO core here. So what first we should see is the Shockwave breakout, as we have said before. First, we have a Shockwave break from the skin of this star. And the duration of this Shockwave breakout is about, you just simply compute it by the radius of this star divided by the speed of Shockwave. So it's about 1 or 2 seconds. Let's see. This part. These are the shock waves. It goes out from the surface, and the supernova occurs. And from the observation of this GRB, this is quite a lucky GRB that in the summer we came here. Then before, only a few days before this GRB happened, and then we did all the analysis in Yale Center, and now the paper is almost accepted. We observed 2 seconds. The emission in the very beginning. With these two, it's very short and not very energetic. And also from the theory that we know the supernova, the shock wave, the kinetic energy of the shock wave is about 10 to 51 erg. 10% of this kinetic energy goes to the electromagnetic emission. So we should observe about 10 to 50 erg for the shock wave breakout. And what we found in this GRB, in these first 2 seconds, is at 7.98 10 to 49. So almost equivalent. Very good for the duration and for the energy. Then we will have the ejector moving, because the ejector is accelerated by the shock wave, and it starts to expand. And then after 10 seconds, from here, we think this from here 2 seconds to 10 seconds is the traveling time of the supernova ejector. Then here, the supernova ejector reaches the companion neutron star. Then acceleration, the accretion starts here, very energetic accretion. So first, we did the estimation. For such from the 10 seconds. We can know the distance between these two stars. So it's about 3 times 10 to 10 centimeter. And from this distance, we can infer the accretion rate. The accretion rate within this 10 seconds is like 10 to minus 3 solar masses per second. And it lasts 10 seconds, 10 to 20 seconds. So we should observe that 10 to 50 erg per second and for a duration of 10 seconds. And exactly we have seen this part. It's about, you see, from a little less than 10 to a little more than 20. And the luminosity is the total energy of 10 to 51. And also we did the simulation. And we put 2 stars here. This is this now it is a neutron star. Before it was that very FACO core. Then after the supernova, the ejector goes out, and the ejector has been created by the companion neutron star. This neutron star is becoming more massive during the accretion, but it did not. During this accretion, we saw this part. So now we have we have a massive star, we have a neutron star. Then after this procedure, we have a neutron star found in the center of the supernova, and the initial neutron star becomes a more massive neutron star. But there is another possibility that if the binary separation is very close, this neutron star will accumulate enough mass and collapse to a black hole. This we will discuss later. So during this procedure of accretion, there are a lot of plasma generated and flow out in this direction, because you see, this is the supernova ejector, and only this part, because of the accretion, we have some low density part. So in this low density part, the plasma can go out, but opacity is not very high. So by solving a lot of these equations, considering the full general relativity, and also because we need to put the initial condition of density profile of this system, so we can compute and we can fit the light curve that observed. These are many examples that we did. The points are the observation, and the line, this red line, this blue line, are the theoretical fitting by those formulas. Also, when we were analyzing the spectra, this is some Monte Carlo iteration to do the spectral fitting, we found a black body, a thermal black body. This thermal black body is about 5% of the total energy. You see, this is the black body, and this is a non-thermal emission from the plasma, this thermal part. But from thermal, we can infer a lot of informations. We can infer the radius first, and also from the evolution of the radius, we can know the velocity. We consider and we interpret that during the accretion, there is a thermal bubble established and expands, and the thermal bubble will reach the speed in the order of the speed of light. So from the theory, we infer the radius from the thermal spectra is about 10 to 10 centimeter, and we have this formula. So the temperature should be around 7 keV, and at 10 to 10 centimeter. And what we observed is the temperature drops from 7.9 to 5.6, and the radius increased from 1.6 to 4.3 times 10 to 10 centimeter, and the velocity is in the order of the velocity of light, so very consistent. Now later we have a new neutron star generated in the center of the supernova. This new neutron star has faster spin. Here let's see first is this blue one. This blue one is from that GRB 1807-28. Then from the distance, before we inferred the distance between two binary stars, they are very close. The tidal force locked on that massive star. So the self-spin period is the same as orbital period. And also we know the radius of a star, which shrinks from thousands of kilometers to 10 kilometers. So we can know the spin of the newly born neutron star. But if we adopt this spin is 2.5 milliseconds. If we adopt this neutron star and we construct a model using the luminosity from the dipole and the quadrupole emission, we can have a fit. You see the blue line of the afterglow of the emission of this system that we observed after 100 seconds. Very good fitting. So this tells us that the neutron star, the rotational energy, powers the later evolution of the system. The red line we will explain later. There's this synchrotron. So how it powers? It from the rotational energy of the neutron star, we only have energy injection. So this energy will accelerate a lot of electrons in the supernova ejector. But also we need to find a way to release this energy. This is by the synchrotron emission. Since we have a neutron star in the center, we know the magnetic field of all the circumstance. Then we adopt a synchrotron model. The synchrotron model is at a very different time. Can so well fit the evolution. This is X-ray, this is optical, this is radio. Radio does not fit well because we did not consider the absorption, self-absorption. Otherwise, they will drop down. These are the GV emissions. They have a different origins we don't consider. So the synchrotron model plus the energy injection by the neutron star can well explain the light curve and the spectral balls. This is because we understand this system before, so we know this kind of system always involve supernova. And so we expected at the first days when the GRB happened, we send a letter to GCN, which is a coordinator network for a lot of telescopes and satellites. We say, please look at that position, that GRB. After 15 days, there will appear the optical signal of the supernova. And indeed, this is the letter we sent. And indeed, the VLT, the Very Large Telescope, found the supernova signal after 15 days. This day, we were in Tsinghua University. We were very happy, and we shared the news with Professor Yao. This is a spectrum of, you can see the blue one. The blue one is a spectrum obtained for this supernova, GRB associated supernova. And the black one is a template of the type 1 supernova. You see, they are the same. So this is a type 1 supernova we have observed. So let's, before we were talking about the system of that the two binary has a further separation. But if we reduce the optical separation, we will have a different system. Those look similar, but finally, this star accretes enough mass to collapse to a black hole. Okay. Now, finally, this is a black hole, and this is a newly born neutron star. And in this system, since they were quite close before, and so the neutron star left has less spin period. It's 1 millisecond the neutron star left in the center as this red line. And also it well fits the late afterglow of the system. The previous energy was from the kinetic energy of the supernova ejected itself, but later it is powered by the neutron star emission. And also in this system, since the emission is very strong, but when you form a white dwarf, you accrete a lot of mass. So you have the emission in this direction. Also, you can see significant emission in other directions. But this direction has a lot of baryonic matter, so the energy will propagate, and it takes a longer time to go out. Again, we established the hydrodynamical equations for such a system because we have the density over here, and we know how much energy is going out. So we can have the answer. This B is the effect divided by like how much mass is here and how much energy injected in that direction. So finally, we can obtain at which time the energy goes out from the system and what the velocity it should be. So this is also the simulation, which this is the density profile of the supernova ejector that is swept by the E plus E minus plasma, and this is the speed. So we expect that at around 100 seconds, we should see the X-ray emission like a flare moving at the speed of a few minor relativistic speed, 2, 3, 4. And indeed, in those strong GRBs, we saw the flares. We see at around 100 seconds, we see these flares. It's not a power, it's a lot of flares. And by doing the statistical analysis of these flares, these are 4 examples. The x-axis is the energy of the GRB. Y-axis, this I cannot see clearly. One is the occurring time of the flare. One is the duration of the flare and the luminosity of flare and something else. So the flare, the property of the X-ray flare is closely related to the energy of the GRB itself. And in this GRB, we see something fantastic. That we did the time-reserved analysis, that we split the light curve to many time intervals, and then we analyze the spectra. And we found the thermal component in each spectra. Here, this thermal, thermal, thermal. So we have the thermal evolution for 100 seconds. And from thermal, we know the radius, we know the velocity. We see something, the velocity is increasing. You see this velocity from 0.4 c till 0.9 c. The Lorentz factor, and this radius also is increasing, which means we are observing that the supernova ejector being accelerated by the GRB, by the energetic GRB. So this normal supernova becomes a very energetic supernova. This explains before that we save 2.6 times more kinetic energy in this GRB-associated supernova. And this is another example. Also, we did another prediction of the supernova appearance for this 130427A GRB, and it appeared indeed. That was 5 years ago. This system forms a black hole, but previously it forms a massive neutron star because the orbital period was too long. So here I finish my talk. And also Riccardo Giacconi, our friend, who passed away how many days ago? 3 days ago. 3 days ago. He established X-ray astronomy, and he got a Nobel Prize for it. So just thank you.
Thanks, Dr. Wang. And now questions?
So I don't quite understand one of the light curves that you show. You have a cursor followed by a big spike after 10 seconds, and so your explanation is that you have a explosion from a bare
here, yes,
ion core.
Yes.
And that gives you the first spike.
Yes.
The cursor.
Yes, here, yes.
So, yeah, I'm just trying to understand because then the blast wave expands and
then the ejector.
Collides with the binary neutron
binary neutron star, yes.
companion neutron star. And why? Then that caused another explosion.
This part.
What is this part?
This part is.
Show exactly the image of the reconstruction.
Okay. But accretion has very high efficiency of converting the mass to the energy,
Yes.
like 14-15%. So this star, the companion star, accretes how many mass? 0.5, 0.6 mass, solar mass. So a lot of mass accreted. So during this accretion, a lot of energy released. This accretion can continue.
So the second spike is accretion.
Accretion, yes, powered by the accretion.
And that's much more.
That's much more
luminous than
the precursor, yeah.
itself.
Because the accretion rate is 10 to minus 3 solar mass per second. Really high. Because at this very high accretion rate, you have the temperature around the neutron star like 10 MeV. This 10 MeV, you can produce a lot of neutrinos.
Is that much larger than Eddington?
Much larger, much large.
And but I don't think we really understand
We,
super Eddington accretion, especially what's the luminosity that goes out of it, because you're using this.
We have done that.
But we have done a paper.
Simulation.
Yes.
With relativistic radiation
Yes.
hydro.
Yes.
It's only because the neutrinos.
Neutrino. Yeah.
Because here are neutrinos that have taken out a lot of energy. Here you have temperatures of
10 MeV, 10, 20 MeV.
at densities of larger than 10 to the 6 at the surface of the neutron star accreting. So you emit
But the neutrino takes away the energy, then the collapse can continue.
not photons.
Not for,
I mean, Eddington limit for neutrinos is something like 10 to the 53 erg per second.
Neutrino is much less.
This has been done by York. All this analysis of hypercritical accretion taking into account neutrino. And that is the beauty, that it fits precisely.
And so this is the relativistic radiation hydro simulation, I guess.
yes. This is performed by Lawler, but he used a computer collaborator with Los Alamos. Los Alamos, they have very good code. Yeah. Los Alamos.
We just published in APJs a huge article showing all these details. But the beauty, this is the one in which the binary period is longer than 4 minutes. Therefore, there is not too much accretion in the companion neutron star, and you see just this spike there. But when the binary period showed the other case is shorter than 4 minutes, then the hypercritical accretion is so big that it creates the black hole. You can show the animation of the black hole.
Yeah.
You have
Yes.
And this is this was done by York and by collaborator. And at this stage, in the moment of formation of the black hole, you have a huge amount of energy, much bigger than the one in the neutron star, 10 to the 54 ergs. And this 10 to the 54 impact on the remnant.
You may see the distance from this unit.
And you can see, as a function of the impact, show again the acceleration. As a function of the impact, the speed of expansion of the supernova change from 0.2 to 0.8 c. Therefore, it becomes a supernova.
Here.
Exactly.
Here. You can see the velocity change.
These are data in which you see the transition from the initial supernova to an hypernova. We code to the system during the expansion.
Okay. And I also wonder, for those kind of simulations, what kind of method are you using?
Of method.
Method.
It's a smooth particle design.
Oh, it's basically SPH.
Yes.
SPH.
To follow the Super-Eddington scenario, I remember in one page you've shown estimated outflow velocity. Is that about 0.5 light speed?
Yes. Here, yes.
Yeah.
Is it here? 0.56?
Yeah, I think it's essentially interesting because in single black holes and neutron star system, we also have super accretion scenario, and actually this measurement of the speed of the outflow is about 0.2.
So very similar, yes. So.
Yeah, similar, and I think the structure of the wing is also kind of accelerating than
I see.
constant.
I see.
So,
Thank you.
just I have another
Yes.
Because I think we don't detect enough of them because the detectability of the X-ray detectors for now is not good enough to see all of them. See some
Yes.
reference.
Yes. That's why I said most, if not all, are from the binary systems.
The work is planning.
Thank you.
I've got a few questions. First, please go back to the continuum equation.
Here?
The continuum equation, not this one, the next one. Yeah.
This one? Not this one. Oh, continue. Yeah, here.
Well, I mean, the momentum continuum equation in the next few pages.
Ah, I see. Because those equations, because we are analyzing a system very close to the black hole, so we did the general relativity one. Here is just the simplified.
Solve the previous equation, not this one.
What's the name of that package we are using?
Where's that?
David, what's the name? Pluto. You know, we have student David. He modified and he wrote additional packages to Pluto. Yes, Pluto is doing the dynamical simulation. A Python code.
This actually, from the point of view of simulation, this simulation has three steps. Okay, the first part, which is SPH, which is the part of the evolution of the supernova and the accretion, and when you can find the accretion rate. Then you have the hydrodynamics in the accretion that is fully general relativistic. That is made in another part of the code. It's another part of the code. Because you have,
is that a grid-based code?
Because you have to in that part you have to have the information for the general relativistic properties of the space-time near the neutron star. So that will make that part from the SPH, because this SPH is Newtonian. We are actually at Los Alamos. They are now working on a new version of that of SPH code, the RSN SPH code, for a general relativistic version to make everything general relativistic for the beginning. Although it is not needed because the accretion starts more or less at between 20 and 50 Schwarzschild radii of the neutron star. So it's actually to compute the accretion rate is not needed the general relativistic part. But to compute the increase of mass of the neutron star, you need that. That part's a part. Then there is the interaction that Professor Ruffini was speaking about before. Interaction of the GRB, the electron positron plasma, with the ejecta is made with Pluto. So it's a third part of the.
Which part is that?
The part, the electron positron plasma interaction with the supernova.
This part.
That's made with
This part.
with
This part.
Pluto is just an MHD code. How do you deal with electron positron plasma?
Why not? No, but Pluto. This is a new part of Pluto. We made available soon in a new article. It's an article by one of our students. We made a new library for Pluto to do these things.
Is that something like MHD peak, combining MHD and peak? Okay.
And a new radiative transfer library for Pluto. Also.
Well, we are happy that you can appreciate this. I am happy that you appreciate these points technically, because they are quite advanced. To me, one of the most beautiful results, which was unexpected until this paper, is that thanks to all these equations, you can correlate the angular momentum, show the afterglow. You can correlate the angular momentum of the binary to the accretion into the new neutron star. The new neutron star is an outcome of our approach, because people did not look usually for the new neutron star created by the supernova and the accretion in it. But when the angular momentum of the binary is very high, the spin of the new neutron star, if the binary period is long, the spinning is smaller than when they are very close bound. And therefore, we can really measure the spin of the black hole for the more energetic source, the red, which has shorter binary period of the binary, compared to the spinning of the new neutron star in the case of a binary period longer.
And another interesting thing is this is initial, like a few days. So in the beginning, actually in the beginning few years, the quadruple emission is higher than the dipole. But the quadruple emission is proportional to omega, where's omega 6, and the dipole is proportional to omega 4. So the emission from the quadruple decays faster than the dipole. So for nearly, I think more than 99% of the neutron stars observed by us are very old, millions of years old. That's why we only see the dipole emission. And always the dipole emission can fit the observation very well. But this new neutron stars, they have very strong quadruple. And this is expected by some theories. So okay.
More questions?
Yeah. I'm curious about the gravity term in your continuum equation. I haven't found it.
You mean I think we did not can consider the
gravity.
We have the metric here, G mu nu here.
I see.
We have G mu nu here.
And another question is about well, in your theories, in your models, is there some problems like the standing shock problems? Or there isn't just a problem like this?
Can you?
What was the question?
Can you say?
In the Kerr-Newmann model, there will be a standing shock.
Oh yes.
But in your model, there won't, or you can solve this problem.
What do you mean for the supernova?
Supernova, yes. Supernova always has problem of how to expel all the shells.
No. This problem is not solved.
Not solved. And
I mean, you have to explode the envelope of the supernova by some method. So in these simulations, we don't care. We assume, okay, we are using the Kerr-Newmann supernova code of Los Alamos. Okay, they use the convective instabilities to explode the envelope.
Well, final question. Maybe a comment. Well, if your model is right, I think there will be more binary system with black holes and neutron stars.
yes, and finally they even may merge to have the short gamma ray burst.
Yeah, right.
Yeah.
So maybe in observations we can find more just examples like this. Gravitational wave observation.
The rate, I think the rate of the binary system.
But the rate of GRBs is low. But you can compute. Actually, we did it. So we published a paper this year about that.
We computed the rate
The
here.
neutron star black hole binaries left by these systems. Anyway, the rate is not high enough to detect them. At least not by light. Not possible.
Okay, I see.
We know what triggers the collision.
What triggers a collision? Collision of what?
Yeah, what of your binary?
The collision.
I want to know what triggers this kind of collision process. Why this binary?
Why the massive star collapse? This is we use the standard theory of the supernova. There's no difference from the supernova type 1b, 1c theory, I think. But it is within a binary system, but this is not very well investigated, I think, how the star evolves within a binary system. But
what triggers the collisions is in these systems.
Speak more clearly with the microphone.
the evolutionary path of these binaries follow two supernova explosions. So you start with the first massive binary, then there's a first supernova explosion. This supernova explosion, you form the neutron star, which will be the one accreting after. Okay? The first supernova creates a neutron star. Then the second, the massive star, the other massive star continue to evolve. And at some point, it will make the second supernova explosion, it will make the supernova explosion again. So at this point of the supernova explosion, by the binary evolution, emission of gravitational waves, common envelope phases, and all these things, the binary will be of a short period. Okay? This is the short period of the binary. And there is the second supernova explosion. It's a second supernova explosion. So it's the material of the supernova that is going to be accreted by the neutron star companion. So it's not a collision. It's a supernova explosion. So it's the normal evolutionary path that a massive star would have, but now in presence of a compact star companion. Is the only difference. But if I understood correctly your question, but I'm not sure. What is the collision you are speaking about?
I thought, yeah, I really, I thought you made the companion.
The evolution of the binary system, we simulate all the evolution, you think? Actually,
I missed, yeah.
we did not simulate all the evolutionary scenario. We did not.
No, but this has been simulated by other people.
By other people, not by us.
Population synthesis code they have.
In your simulation scenario, it's just they are accurate enough for a second supernova.
Oh, this we simulated. Yeah, only for the second one we simulated, not the first one. Many people did it for the first supernova in a binary. Usually the mass of the type of 1C, like initially you have 25 solar masses.
Let me see if I understand. Okay, I can try to explain.
Let me see if I have other slides. Wow.
So you start with a massive binary. Okay? So you have one of M1 and M2. Okay, 1 and M2. Then this star. Let's assume that M1 is larger than M2. Okay, let's assume this. Then this first more massive star will explode as supernova. Okay, will make a supernova explosion. Then from this supernova explosion, you create a neutron star. Okay, you create a neutron star. Then this star continue to evolve. Then you will have here, this is still an ordinary star. Then at some point, this system continue to evolve. This can lose mass by binary interactions, as one you explained, and becomes a carbon-oxygen core star. And at some closer.
Yeah.
There can be, may happen many things in between these two systems. There will be a common envelope phase for sure. This we know, at least one common envelope phase, namely that this star expands and embrace all the system with this matter, and this matter is after ejected. And then you have this carbon-oxygen core here with the neutron star companion. Then this system, this star evolved, this star made a supernova explosion. And this is this supernova explosion here. Is this matter which will be accreted here. And this is our simulation. So this is the simulation we are making. And there are other codes, population synthesis codes, which have made a population of this kind of binaries, but it's not our work. So in which we show that if you start with some masses, of some given masses, for example, from, let's say, 10,
20,
15, 10 solar masses, okay, for example here, then you will end with a neutron star of 1.8 solar masses, let's say, and this carbon-oxygen core of 9 solar masses or so, something like that. Okay, there are these codes with a binary period of few minutes. These simulations are apart. We are taking care only of this simulation here, of this system. Clear now?
Another question, you just mentioned that when you solve supernova explosion, when you simulated supernova explosions, you just use the previous code. For example, you just solve the one supernova, right? You didn't consider the companion stars effect. Well, actually, I recently read a paper. It's a theoretical computation. Well, he gave a statement that the asymmetry of the turbulence or the core or the something else can help to break the standing shock. So my question is that, have you ever tried to add the companion stars effect in the supernova explosion simulation?
We did not try, but I think from observation of the type 1c supernova and from the polarization, it infers it's not symmetric. The system is not symmetrical.
We did not try, but we made simulations with asymmetric supernovae in our last paper, just publishing now in Astrophysical Journal. So we try both spherical, but also asymmetric supernovae, both of them.
Any other questions? Okay, I'm glad that we had the expert discussions, but I hope you actually have the mood to answer a non-expert question. I just wonder, since we observed already a lot of supernova and gamma ray bursts, and some of them, if I understand correctly, are very far away. And we also know that actually dark matter composes most of the matter in the universe. It just occurred to me, I mean, is there any possible interaction or interference on this observation of supernova and gamma ray bursts from dark matter?
I think I read some papers discussing this issue, but there's no very confident observational evidence. I did not see.
But it depends on the kind of interference that you mean.
Say, for example, I mean, is that possible to say the gravitational lensing effect? Or does that even some factor that even worth taking?
There are a couple of examples in supernovae, from supernovae. From GRB, I think it was discussed on, no, it was adopted on one GRB that I remember. Yes. It might be, yes. It might be.
Yes. Of course, I don't know if you were here when I spoke the first lecture. The most spectacular thing could happen. In our opinion, there are two kinds of dark matter. The dark matter cluster of galaxies, the one that you are speaking about, the lensing. But in our opinion, also in the core of our galaxy, that is not a black hole, but is dark matter, a huge concentration of dark matter. Therefore, if you would have a supernova there, this binary, a gamma ray burst there, it will be incredibly important. And I think it could happen. It could happen.
So, possibly say some other effect besides
completely. No, you will really see the real cross-section with dark matter. This amount, huge amount of concentration. It's a beautiful possibility. Because there are binaries down there, many, the galactic. And if there will be one of those giving a GRB.
Yes, I remember that with supernovae, they were able to predict where a supernova would appear after from the lensing.
I think this for dark matter. There's another usage of the GRB because it is very far away, is to test the quantum gravity. We know from string zero or the loop that there could be the dispersion of the velocity for different energy of photons. And from observation, we can see if all the point emission, two photons coming generated at the same moment, and it travels the whole universe time, and then it reaches us. we will see the difference arriving time of these two particles, two photons with different energies. Then we can constrain the quantum gravity.
In short, you actually want to measure if photon has rest mass 0.
Also, it can be, yes. But now I think the result is not very good. At least the first order is the energy of photon divided by the Planck energy. The first order is not clear. It seems there's no such effect. And we should go to the second order.
Okay, any questions? If not, let's thank the speaker again.
This is a spectacularly good idea. If we arrive that there is in the galactic core concentration of dark matter, not of black hole, then the occurrence of a gamma reburst in that region, of course, will be a little problematic for our galaxy, but very, very interesting for physics. And maybe that is the sort of physics that it will be very worth to check in nearby galaxy. I mean, to look for galaxies similar to ours, with 10 to the 7, 10 to the 8 solar mass core, and keep watching if there is a GRB happening nearby. That would be spectacular, because it will be a way to shake the ENOS and to really see the interaction of dark matter with this would be spectacularly important.
Yeah, I think it's good to use the short GRB, because some short GRB are in the halo.
Yes.
Some are in the very center of the galaxy.
Yes.
So you can see the difference between these two groups of the short GRBs.
Okay, good.
Very, 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 very beautiful idea.
If one day you got Nobel Prize for that, I mean, consider having me for a share.